Welcome to module 50 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about concurrency control, and in the last module we took an understanding of the locking mechanism and protocols, particularly the two-phase locking protocol, and realized that while the locking guarantees isolation, locking does improve on the serializability. Locking ensures that we can have consistency all the time, but it has a big problem of deadlock, and that can happen very often, very easily, even in small examples and so on. So, the question is how do we detect deadlock, or even better still, can we take strategies to prevent deadlock or recover from deadlock? And because we will have to live with deadlock, there is no other option, right. So, also there could be some simple protocols which can avoid deadlock itself. So, it is primarily about deadlock handling. So, deadlock system is deadlocked, again just to remind you, if there is a set of transactions that every transaction in the set is waiting for another transaction in the set, right. Simplest can happen between two transactions, but it can happen between multiple transactions. So, deadlock prevention is a protocol that the system will never enter into a deadlock state. So, can we guarantee that? Can we do something to prevent the onset of the deadlock? So, this could be require each transaction locks all data items before it begin transactions, usually difficult, and particularly if a transaction is dealing with large number of data items, and may significantly reduce the concurrency in the system. We could also impose partial ordering of data items and require the transaction can lock data items only in the specified partial order. So, these are some of the strategies, we will not go much into them. Now, a pair of strategy for deadlock prevention which is very effective, it is based on timestamps. So, what is a timestamp? A timestamp is a unique identifier which is created by the database to identify the relative starting time of a transaction. It may not exactly be the clock time, but it just says which transaction was earlier, which transaction was later, depending on when that transaction started executing. Right. So, it is a method of concurrency control which can use this transaction timestamp and make certain very effective strategies. There are two schemes which use transaction timestamps to prevent deadlock. One is non-preemptive, called wait and die scheme, and one is preemptive, called wound and die scheme. Philosophically, very simple. Non-preemptive means that you be well behaved. So, older transactions may wait for the younger ones to release the data item, but the younger transaction never wait for the older ones, they are rollbacked immediately. Preemptive is where an older transaction, instead of waiting for a younger transaction, kicks it out, owns it out, but a younger transaction may wait for an older one. So, this is the philosophical. Let us look at it in formal terms. So, in non-preemptive, let us introduce the notation. The transaction T n is requesting for a data item held by transaction T k, right. So, T n is allowed to wait only if the timestamp is smaller than that of Tk. What does smaller timestamp mean? That Tn started earlier, so it is a older transaction. Otherwise, Tn is killed. So, what we can say in mathematical terms, if timestamp Tn is less than timestamp Tk, then Tn will wait while Tk is using that data item till it is available. But if it is more, that if it is newer, then Tn is killed immediately. And what you do? You restart after a random delay. But in that way, what will happen? A younger transaction will get even younger. So, to stop that, when you restart, you do not restart based on the current time when it is restarting, you use the same timestamp. So, I mentioned the timestamp is indicative of the order, but is not exactly the clock time. So, it is actually starting at a later time, but I am using the older timestamp so that the seniority, the relative seniority of that transaction remains, though the transaction has not been doing anything. So, as if the transaction was sleeping during that time. So, it allows the older transaction to wait and kills the younger one. Here is an example which you can see for yourself. This is called the wait die scheme, where things are non-preemptive. In the preemptive scheme, you do differently. The transaction Tn again requests a data item held by Tk. Tn is allowed to wait if it has a timestamp larger than that of Tk. Right? That if it is younger. Otherwise, Tk is killed. The transaction which was holding that data item, that itself is killed. That is why it is preemptive. In the earlier case, we were killing the requesting transaction. In this case, we are killing the transaction which is holding it. So, if we look in mathematical terms, if this is the case that Tn actually is older, senior. So, it is like you are sitting, you are in a room and there is one chair and you are sitting there. So, if you are someone senior in your family would enter the room, you will leave the chair to that person. Tk is kicked out. But if someone younger would come, you will continue to be in that chair as long as you want, and only when you leave that younger person can take it. So, that is a basic difference. So, the Tn forces Tk to be killed because Tn is senior in the timestamp, and again Tk is started after a random delay with the same timestamp. Otherwise, the Tn will wait until the resource is free, right, if it is. So, this is the preemptive scheme called wound and wait scheme. Again, small example, you can see it for yourself. So, these are very nice simple schemes to ensure that deadlock will be prevented. Other time based schemes include like a transaction might wait for a lock for a specified amount of time. If it has not been granted, then the transaction rolls back and restarts. Obviously, since the transaction by itself is, so this is kind of transaction committing suicide and coming back as a phoenix bird after a while. But certainly, this will ensure that deadlock is not possible, but the starvation is still possible. You may keep coming back and not find that resource free, because since you are going out of the system, you are not waiting, the time when the lock is released and the data item becomes free may not be the time when you are around and somebody else come and get it, right. So, it is difficult to have a estimate for what is a good value of this time interval and so on. So, for these reasons it has been used, but again not very. The next question, this was about prevention. The next question is how you detect. Detection is actually very simple. It is very similar to the precedence graph idea. So, if a transaction waits on another, T I determines T j, then you draw an, so you create a graph where transactions are vertices and you have an edge for every waiting dependency of the transaction. So, if T I requests a data item currently held by T j, so this is the requesting edge, and the graph that results, and it is regularly updating, certainly it is a dynamic graph. So, as the requests are coming, the locks are being granted, they are being released, always this graph is getting updated. But you will know that the system is in deadlock if and only if this wait for graph has a cycle, right? Otherwise it cannot be, because then it is an acyclic graph and the topological sorting has a way of actually allocating the locks, as we have seen before. So, this wait for graph is a good mechanism to dynamically keep track of if a deadlock has happened, because the system has to know that the deadlock has happened. Deadlock does not end. So, unless the system can know immediately, it will not be able to decide to tell the transactions to roll back, right. And then there are further questions in that. So, now when the deadlock is detected, then some transaction will have to be rolled back. There has to be a victim, right. Now, how do you select? Because if I have a situation that this is T I, this is T j, this is A, this is B, that is T I has requested for A, for which T j is holding the lock, T j has requested for B, for which T I is holding the lock. Then the only way to break this deadlock is either to kill this transaction, roll it back, or to kill this transaction, roll things back. As we do that, then the corresponding data item gets released and the other one can get it, right. So, one way to say that in principle what you want to say that you should look for minimum cost, right. So, one is also to determine how far to roll back. So, it could be a total rollback, which is about, or you could roll back the transaction only to as far as necessary to break the deadlock. How far is necessary? Is to release the lock for which the other transaction is waiting, right. And that is kind of the concept we discussed in terms of save point. This is basically, this is done in a similar manner by the lock points. So, you have to roll back to that lock point which has caused this deadlock. There may be several lock points in between which did not cause the deadlock, but once you have got the, that is the reason I was writing the data item on the arc, because you will also need to know on which data item this has happened. So, if I have this situation, this T j and this is T I, this is A, and I have this on B, and so T I is waiting on T j who is holding A, right. So, if I decide to roll this back, then in T j there will be some point where I have x lock A or S lock A, and then there may be another several other locks on several other items, and this is the point where actually you have found the deadlock. So, at least you will have to roll back up to this point, because unless you release this lock, that deadlock cannot go away. So, if you roll back less, it is not enough, you still have the deadlock. But if you have gone to that lock point and released this and have done enough to do this rollback in Tj, it is sufficient. You do not need to always totally roll back, abort and roll back the entire transaction. So, these are the trade offs, different strategies that you can actually have. The starvation would happen if some transaction is always chosen as victim, right. This is always possible. So, what is done to avoid that is you include a cost factor in terms of you are doing minimum cost, right. So, include a cost factor which will keep track of how many rollbacks you have done, right. So, a transaction which is getting rolled back more number of times, the cost of throwing that transaction out becomes bigger. So, eventually that transaction will come in and the starvation will end, right. So, and you can see that here the basic strategies like this wait for graph or comparing time and doing things are relatively elementary, common sense, and rest of it are basically a variety of heuristics which you basically rule of thumb which people have tried out and seen okay this is getting an absolute theory with the generalization of all transaction, all type of operation, all types of data, all types of concurrency has so far proved not to be very successful, but these strategies are very effective and that has made so much of distributed things possible. Okay. Before I close on this, let me also present a little bit of a different way of managing the read write, which can be useful. So, what we say is again each transaction has a timestamp as it enters the system. An old transaction Ti has a timestamp Tsi, another has Tsj. So, you have this Tsi is less than Tsj. So, Ti is an older transaction. Now, here this protocol says that you will manage the concurrent execution based on the timestamps. Earlier we were using timestamp to like in wait die or wound die, we use timestamp to decide who should wait, who should not wait, who should be killed and so on, or we used some of that to commit suicide by a, but here we are saying that the timestamp will decide the concurrency. So, for that it maintains two different timestamp with every data item q. This is called write timestamp and read timestamp. This is the last time that this data item was written is a write timestamp. So, it is the largest timestamp, which means the most recent write of that data that was successful. Similarly, the most recent largest timestamp of any transaction, you do not care which transaction, but any transaction, what is the latest time that q was written, w timestamp q, what is the latest time r q was read, the largest time, latest time for read. And then along with the timestamp of the transaction, you decide on when to proceed, when to roll back. Suppose now, so I have the transaction Ti and it has a time stamp TSI. I want to do a read. Right. Now, when I want to do a read, what do I need? I need to use a data which is correct, updated, recent. Right. So, there are two conditions possible. This may be less than the right timestamp or this may be greater than the right timestamp. If it is less, what does it mean? That this transaction was started before this write happened. Right? So, TI needs to read a value of Q that is already overridden. Because that what is W timestamp? Is the last write, the time it was last written. So, your transaction is older than that, right. So, it does not make sense to do this read. So, the read is rejected, TI is rolled back. On the other hand, if it is more than W timestamp, then the read operation is meaningful. That is, your transaction started after this write happened. So, that is the latest value, and therefore, now you are using a fresh value, not one which may have been invalidated later. So, the read is allowed, and since you do a read, the read timestamp of Q has to change. Right? Now, what will it change to? The current time, this is the transaction time that this transaction has. Right? This is the time of the transaction after that, right. So, it could be that, or it is possible that it has a read timestamp which is higher, right, which means that it was a write, then you had TI, then you had read. Right. So, it will, when it does that, it will take the maximum of these two. This is your protocol to read. What do you have to do for write? You want to write this. Now, if TSTI, the timestamp of TI is less than the latest read time, which means this is an older transaction. So, you are trying to change a value which has already been read, which was needed previously. So, the write has to be rejected. If TSTI is less than the W timestamp, so this is an older transaction, after that transaction Q has been written, that is the reason it is more. So, it is trying to write an obsolete value, right. So, this also should be rejected. So, what means that if TSTI is greater than read timestamp as well as write timestamp, it is more recent than both of these operations, then only you will be allowing a write operation. And naturally, as you do the write timestamp would be set to the TSTI. Very simple time based protocol, easy to implement, easy to understand, and but it guarantees that you will not have deadlock, and you are having the serializability according to this. For example, here you are these are different transactions, and from the first statements you will know what is the start time. For example, this read z. This read z. So, at this point what will be the read time? The write time for z is this one, right? And what is the time for this transaction is T 2 here. So, T 2 is an older transaction, and after that this has happened, write has happened, right. So, this read was intended to be, the fact that it is happening now is because you are having the concurrency, but it is intended to be here. Right? You are getting the point. It is not that it is here, not that because this gap is not desired by the transaction. In the transaction is read y read z, right? You have write y write z, but because of the concurrency, this transaction did not get to work. It did not get the processor, CPU. Other transactions worked. So, when it is getting this, its intended time is attributed at the beginning of the transaction, which is old. So, it needed to read the data then, but that data has changed in this write z. So, this read is not valid. So, you abort. That is the kind of logic. Similar thing is happening here in this write. So, this is your transaction start state. So, it should have happened here. If it would have happened here, then T 4 would have read something different, but T 4 has already read this. So, now if you change, then you are getting inconsistent with T 4. So, you cannot allow this write to happen, you abort. You check the other cases, they satisfy, and therefore, those will not be aborted. Right. So, this time based protocol guarantees serializability, because all are in terms of transaction with smaller timestamp is dependent for something which for transaction with largest timestamp. Right. So, there cannot be any cycle in this precedence graph, and that ensures freedom from deadlock as no transaction ever waits. But this schedule may not be cascade free. In fact, there are given instances where it is not even recoverable. So, those are some of the other perils that you come in here. Okay, with that we come to the end of this module, and we have discussed about detection, prevention and recovery, partly just glimpses from deadlock and a time based protocol that guarantees a deadlock free processing. So, these are some of the different strategies which enhance the concurrency while keeping deadlock under control for better throughput of the transaction processing system. So, with that we will close this week's discussion on transactions and concurrency, and get into a new topic in the next module next week. Thank you very much for your attention. See you in the next module.